So here we have the position of a 50-gram oscillating mass that is given by x of t is equal to 2 centimeters times the cosine of 10 of t, where t is in seconds. And then they ask us to find all of this stuff. Well, it's a lot of stuff, but it's not too bad once you get the hang of it and once you get in the thick of it, so let's just get right onto it. So for part A, well, first off, we know that the equation for simple harmonic motion is given by x is equal to a cosine of 2 pi ft. And if we directly compare these, we can see that our 2.0 centimeters is equal to a. It's a thing that we multiply the cosine by. So we can just conclude that a, or amplitude, is equal to 0.02 meters. And this makes sense, by the way, because we know that cosine is a function only oscillates between 1 and minus 1. So if we multiply it by a, then the function x is only going to oscillate between a and minus a, which makes sense based on what we know from simple harmonic motion. It should only oscillate between its amplitude and its minus amplitude. Alright, so for part B, we can just look at this equation again. We see that the thing that we're multiplying the t by, the 10, has to be equal to 2 pi f, because you can see that our t's are the same in both. So we know that our 2 pi f has to be equal to 10. And then if we do some finagling around, we know that f is equal to 1 over t, excuse me. So we have this expression, and then we have t is equal to 2 pi over 10, or pi over 5. And then if we account for our sig figs that are given to us, they look like there's around 2, so we're going to write 0.63 seconds. And again, we know we can safely do this because we know that t is in seconds, and seconds is an SI unit. So to cancel that out, this 2 pi f has to be in 1 over seconds, or hertz. And so this thing that we're doing here does make a little bit of sense. For part C, we're trying to find the spring constant. Well, we know that t from our equation chart is equal to 2 pi times m over k. Now this is a handy equation for us because we know t, we calculated last part. We know m because it's given to us in the problem, and we don't know k. So we're here given all the stuff that we needed to know to solve for k. So if we do some algebra, we can see that the square root of m over k is equal to t over 2 pi. And then if we square both sides, and then we get this, and then if we cross multiply, and then we do the final division, and I'm just going to do this in my head real quick, we can see that k is equal to 4 pi squared m over t squared. Now all we have to do is plug in the stuff we know. M is equal to 0.05, and t is equal to 0.63. And this should be equal to 5 newtons per meter. Now we're converting the mass into kilograms because, again, we want to keep everything in SI units. So here we have a 50-gram mass, so converting that to kilograms, that would be 0.05 kilograms. All right, part D. The maximum speed. Okay, this one is just an equation we learned in class. We know that Vmax is equal to 2 pi f, a. Now, in this equation, we would normally have to find f by just looking at the things we went before. We have period, so we can just do 1 over f. But in this problem, we can cheat a little bit because we know that 2 pi f is equal to 10 from up here in part B. So therefore, we can just plug that in, and we know a has 0.02, and then we can just get 0.2 meters per second. So this basically just illustrates what we're trying to do with this entire problem. If you find stuff that you know that might help you that you did in other problems, use them, especially when you're doing multi-step problems like this. They're usually constructed in a way that your past answers will try to construct upon and will help your answers in future sections. And this is also true on the AP test. So keep that in mind. For part E, we know that the total energy is going to be equal to the potential energy. Oops, this should be US because it's a spring, and K is equal to K at its max. Now again, we don't quite know. We know that K is equal to 1/2 mv squared, and we don't know V, but we do know everything in US. We know K and we know X. So what we can do is we can just pretend K doesn't exist for now and just use the expression for potential energy. 1/2 kx squared. So, and note that this isn't any x, this is x max, right? Because we're talking about the maximum potential energy when we're taking the mass and we're pushing it the farthest back it can possibly go. So, what do we know about the farthest back it can possibly go? That's the definition of amplitude. So what we can do instead is erase this x max and replace it with a, because again, the x max, the displacement, is just the definition of amplitude. So what we have here is two things we already know. We know K and we know A. So we can just do a quick plug-in over here. And then we get 0.001 joules. If you want to be a little extra, we know that this is 1,000th of a joule, and a 1,000th of a unit is a milliunit. So we know that this is equal to 1 millijoule. And again, you don't have to do that. That's just me being nice and neat. All right, let's scroll down a little bit. So, in part F, we're going to be asked to find the velocity at t equals 0.4 seconds. Now this one's a little bit trickier because this 0.4 seconds isn't necessarily a point where the kinetic energy or the potential energy is equal to 0. Because we know from before in part E over here that I just neglected writing the K and the US terms here because we know that they're 0 in each one of these cases. So US is max, for example, at its maximum displacement from the equilibrium position. And kinetic energy is equal to 0 there, so just didn't write it. And then for K, we know that the K is at its max in the equilibrium position, so we know that we don't need to write potential energy there because the potential energy is 0. But we know that at t equals 0.4 seconds, it might not be in one of those positions. We don't have enough information to make that assumption. So when we write our equation, E total, we have to write US plus K because both of them have to be some value, and both of them are some value, and we're going to see if we can use them to calculate anything. So let's just write this out with the equation subbed in. And again, we can't use the trick where we replace x with a or we use v with vmax because we don't know that if they're at their vmax or their a, and it's not safe to make that assumption. Well, what do we know then? We don't